So in this lecture, we're going to look at 3.1, 3.2, and 3.3. Now I had already posted an applet for 3.1, the box problem, and I encourage you to take a look at that and use that little applet as a virtual way to manipulate and kind of see what happens as you change different cuts to the box. But let's go ahead and move forward and just get into the activity. Okay, so the box problem. Box problem starts with a piece of paper, cardboard, something. In this case, we're taking an 8.5 by 11 sheet of paper, and what we're going to do is we're going to cut squares off each of the corners. So notice there are 4 corners being cut off. So what happens is kind of like the burning the candle at both sides. As we make a cut, 2 of those cuts are subtracted from each of the dimensions of the paper. The edges are folded up and then a box is created. And again, you can take a look at the applet that I sent that will actually animate this. So cutting 4 equally sized squares from the corners and then folding them up, we can actually make a box. And you can do this physically. Part of the thing is go ahead and get a piece of paper, give it a try. The question is, do the cutouts have to be squares? I guess you could do rectangles, but then one side might be higher than the other, right? If they're going to, the height of the box is going to be the same, then really they need to be squares. But it depends on, you might want to be creative, right? But to get a nice square box for storing things, we would want it to be a square so that the height of the box is determined from that cut. The quantities that are going to vary, the larger I make the cut, the width and the lengths are going to change, become smaller, right? Because I'll take more of the cut. The less of a cut I make, the more length and width I have, but then the height is less. So again, play with the animation, but what we're stuck with is the paper doesn't change size. So we're kind of stuck with that. Okay. So what happens to the box? So if I make a shallow cut, make X kind of, I get a shallow box. To get a deeper box, I have to make deeper cuts, and it's not as wide. So the length of the sides of the squares increase. What I start to see is the base becomes, the area of the base becomes smaller and smaller. Okay. So how would it look like if, using that animation, if we went from 0 to 4.25 inches in cuts, and now no, 4.25 is half of 8.5, so that's as far as you can go, because if you go any further, you've used up all the width of the box, right? So so we're gonna vary the cutout. If it's less than 2 inches to 4, the volume of the box decreases. So there's a place where you get sort of a maximum volume is what's going to happen. And what we see is that we get this sort of cut, and we get a maximum about here, but certainly we lose volume as we make a bigger cut than that. If we don't make a big enough cut, we don't get the maximum volume. Again, all depends on what we are putting in the box, but if the idea is to get the maximum storage capacity, then we want to find the cut that will do that. Okay, so if you've got a box, you can use a ruler. Go ahead and, if you've actually made one, you can see what happens. And then we can complete a table. So if we make no cut and we've got a 8.5 by 11, then 8.5 by 11, but it's got zero volume because there's nothing to fold up. It's just a flat piece of paper. If the width is now 6.5, notice that means we subtracted 2, and remember, so there was a cut of 1 inch on each side. That's the only way we can get this. So it's kind of making up. So we have a cut of 1. So if we cut 1, then also we're going to cut 2 inches off of the length, right? 1 inch on each side. So that gives us a length is going to be, should be 9.5, right? The width should be, it's 8.5 by 11. So there's an error right here. This should just be 11. So there we go. I can't edit this, so we'll leave it at that. And then when you calculate the volume, length times width, length of 9 times the width times the height gives us 58.5. Now if I do a cut of 2.5, that's going to take 5 inches off the 8.5, right, to 2.5 twice, so that there's only 3.5 left in the width and 6 inches left in the length. When we multiply those together, we get the volume is 52. So notice a cut of 2.5 has less volume than a cut of 1 inch. 4.25 leaves no width, does leave some length, but whenever we have 0, we multiply, our volume's still going to be 0 because there's nothing it can store. It's a flat piece of paper again. If we got the length down to 2, the only way we could do that would be to have an impossible cut here, so that's not going to work. Okay, so how do we explain the relationship between the length of the side of the square cut out and how the width of the base of the box is related to the length? Well, what does that mean? Every time we make a cut, we are subtracting twice from the length and twice that cut out from the width. Okay, so, and again, we could see that from the picture that there's a cut on each side. So when you actually do this, it makes a lot of sense. Whatever that cut is, it gets subtracted twice, 2 times that cut. And again, these PowerPoints do go ahead and kind of slowly get you through. So 8.5, we're going to subtract whatever the cut is, we're going to subtract 2 of those. So that will give us the width of the box. The length of the box will be 11 minus 2 times the cut, so minus 2x. That gives us our length. And then what's our height? Our height is going to be x, the amount of the cut. And so we multiply those 3 things together and we will get the formula for the volume, right? Length times width times height. So in this case, 8.5 minus 2x times 11 minus 2x times x. So we can see that it ends up being, when we multiply all this out, we end up getting a quadratic function, although we're going to encourage you to use a graphing calculator to do this and to do these calculations. Okay, and so you don't have to multiply it out, you just enter it in. And you could put in various sort of guess and check. So what if we made a 1/2 inch cut? We could plug in 0.5 for x, multiply it all out. We could put in 3 inches, do that, multiply it all out, see what kind of a volume we get. And, you know, so we could kind of guess, you know, what would be the best one. Well, maybe about a 1.5, as we saw before. So from the animation, again, go ahead and take a look at the graphs. It has a lot of activities you can do there. So if we look at a 0.75 would be when x, the cut is 0.75, the volume is going to be 49.875. We choose another point, say 3.5, that means that the cut itself, the squares being cut out, is 3.5 inches, and it yielded a volume of 21 inches. So the x is the amount of the cut, the length of the cut, sides of the square that was cut, and the y value is always going to give us the volume. Okay, so we can see that as we graph it here, we see these various points. if we want to maximize volume, what we want to do is we want to find where this vertex is. Now, if you see this on your graphing calculator, you'll probably see some part over here, which would be like negative cuts and really is meaningless, which often happens with mathematical formula, that there is a particular domain where they're defined, and then everything else, even though this graph will come down here, it's really meaningless at that point. Because what does it mean to have negative volume? Not really sure it has any value in this particular problem. Okay. Okay. So if you created a box, you could identify, which one is yours, how much of a cut you did, and you can see it. It changes depending upon what cut. So if you did a 0.5 cut, you only had 37.5 cubic inches, but a 0.75 has greater volume. Okay. As you increase from 1 to 3 inches, how does the volume of the box change? Well, it decreases actually. Overall decreases, but even from 1 inch, it'll go up a bit and then comes back down. As you increase from 2.1 to 2.7, what you see is, again, at 2.1 you get 61 cubic inches, and then keep going to 2.7, you only get 46. So we kind of see these average rates of change going here from a particular point to another point. But again, the whole idea generally for this is we want to find the maximum volume. So where is the volume decreasing? Certainly from 1.585 to 4.25. So from the maximum point down to there, we're going to see decreasing. So using the calculator, you can solve for the length of the side of the square cut out of the volume of the box is 62.5. So what you're doing is you could put in a horizontal line at 62.5, and then you'd find that you can do a cutout of either 1.1 or 2, that both of those yield a volume of 62.5. And then using the calculator, we can do it for other values as well. Okay. And maybe I'll go back and I'll demonstrate how you can do that. Let's do this. So again, the volume that we're going to get, I'll put it as a function, is, remember, 8.5 minus 2x, 11 minus 2x times x. And we see this, this at 4.25 or there. So we do go up, and what we want to do is let's zoom in a little bit more. A little bit more, so we go pretty high. The other thing with this, let's get that out of the way. I'm going to have our y-axis go from, let's say, negative 10 to 75. Oh, maybe we need to go higher. Let's go to 100. Whoops, that's the x. Actually, okay, so this is the x. So we could go from 0 to 4 point. Let's go to 5. Okay, that's really all the further we need to go. The y-axis, maybe negative 5. This is the one I was thinking. Let's go to 70. There we go. So now we get this nice flow, and we can see 1.85 is going to give us the maximum. To answer these other questions that they want, 62.5, what we do is we put in an equation for y equals 62.5. And then you see where it intersects. And again, there's videos that will show you how to do this with the TI-84 calculator. And if you send me questions, I can make a brief video on that. But I want to show you, you could use your Desmos as well. It's a quick, easy way to see that 1.175 and 2.033. So that's how they got these values here. Now if you want to see the volume of 23, you do the same thing. Y equals 23, and then you can get those values here. So it's where that's intersecting. So a cut of 3.4 or a cut of 0.277. Let's make it 0.28. All right, so we'll kind of keep moving forward through this. We got that. We could actually get a maximum value. Now here's another problem. They changed the size of the paper. It's a 12-inch by 18-inch sheet. So again, we could very easily do that by coming to our Desmos. Instead of 8.5, we could make this 12. And again, it's the same thing, 2x coming off of here. And this would be 18. And then you could, you've got your graph now. And obviously you can get a greater volume because you've got more to work with. And you can see right here will give you, you'll get a maximum volume of 228 cubic inches with a cut of 2.3, 2.4 I guess if you rounded it up, right? Okay, and so that's the values they're getting here. And again, we go through all of this again. We just make that adjustment and we're able to use our graphing calculator to analyze. So that's really the point behind all of this. Again, the X is the amount of the cut, how many inches we're cutting. The Y value always gives us the volume. So what's our volume? What's our formula? Again, we just take the dimensions of the paper since we're cutting out 2 corners on each of the lengths. We subtract 2x, and again the height is x. So we've done all that. And again, we can find all of these again. And I'm just going to kind of keep going. Yes, once we're at the maximum, we decrease. It's increasing before that. So from 0 to this cut, it increases. From this cut of 2.35 forward, it decreases. And notice it'll go all the way to 6 because you can cut halfway through. So if you got the shortest length kind of determines that. If it's 12 inches is the shortest length, the most we can cut is halfway through. And again, when you do that, you actually get 0 volume. Okay, so now we're into 2.2. So I'm going to take a little break here so we have separate videos.